Hello everyone. We are going to review the molecular geometry today, and the molecular geometry is determined by the VSEPR model. So VSEPR stands for valence shell electron pair repulsion model. So it is based on how the electrons repel each other, determines the geometry or the shape of the molecules. You will find these blank documents on Canvas and also attached to this video. So the VSEPR model describes the shape. If you model describes the shape, which is the molecular geometry, that's the term we are going to use for shape of molecules, based on the repulsion between shared electron pair and unshared electron pair. The unshared electron pairs are also called as lone pairs of electrons. The molecules take a shape that minimizes its repulsion of electron. Now, the shared pair of electron are all electrons repel each other. So they will position in such a way that it has the least amount of repulsion. So the unshared pair of shared electron pairs occupy a larger space than the shared electron pairs because they have two electrons which are negatively charged. Plus they push, so they're going to push each other away as far as possible to maintain least amount of repulsion. The shape is also determined by referencing the central atom, and in Lewis dot structure we also saw what the central atom is, and if you have questions, look at the video for Lewis dot structure. The total number of electron pairs compared to the total number of bonding electrons. So electrons pairs could be left over after the bonding molecules form. So the lone pair, okay, the bond angle is the angle between the central molecule and the outside molecule. So if there is a central molecule attached with the outside molecules, so if I have 4 HH bond, then this is the bond angle between the central molecule and the outside molecule. So if you want to visualize, if you're taking a number of balloons and tying it together, it is similar to balloons being tied together. The more balloons you have, and you try to tie it together, at the end they will try to push apart to allow maximum separation. That's how the molecular geometry works too. Okay, so let's start with examples of different molecular geometry we have. The first one is HCl. So the first thing you have to do is draw a Lewis dot structure. So for HCl, we learned how to draw the Lewis dot structure. So this is the Lewis dot structure. So in this case, there is no central atom. So there is no central atom here, and so no lone pairs. So this is going to be a linear shape. And the way you can draw the geometry is like this, and the bond angle is 180 degrees. Now if you look at your molecular kit, that is how the linear is going to look at. So no matter how you attach it, it's going to be a linear shape with 180 degrees. So the second molecule is carbon dioxide, and if you remember your Lewis dot structure, this is how it looks like. So here the central atom is carbon. So number of atoms attached to the central atom is 2. Number of lone pairs on the central atom is 0. So this shape is also linear, and I'll show you in the modeling kit how it is. So this is your carbon in the center and oxygen at the end, and they are connected with a double bond. So this is also a linear structure. So I have a carbon here and 2 oxygens attached, and each oxygen forms a double bond with carbon. So if you look at the lining of the 3 atoms, it is in a linear form. So that's why the structure is linear. Okay, the third molecule we are going to look at is H2O, water molecule. Here oxygen is the central atom. There are 2 hydrogens attached, and the oxygen has 2 lone pairs if you draw the Lewis dot structure. So here the central atom is oxygen, there are 2 hydrogens attached, and there are 2 lone pairs on the central atom. So this shape is called as bent, and we'll see how that looks. So I have here 1 and here 1. Okay, so this is a bent shape. So see how they are not, this is oxygen, these 2 are hydrogens. See how they are not aligned in a straight line. So if I look at this one, it is bent shape, and you can do oxygen on the top. And so what happens here is, because there are 2 lone pairs on oxygen, they push down the bonds. So instead of being a linear, the bonds are pushed and it is bent. So this one is a bent shape with a bond angle of 109.5 degrees. Okay. The next one is BF3. So BF3 we are going to draw as boron in the center and 3 fluorines. Remember, boron is a special atom. It is happy with only 6 electrons. So boron bonds with only 3 fluorine molecules. Because fluorine is highly electronegative, it won't form any double bonds because it is not going to part with a lone pair of electrons. So the central atom here is boron B. It is attached to 3 fluorine atoms. There are no lone pairs on the central atom, and this shape is called as trigonal because there are 3 bonds, and planar. So if you make a molecular, and I'll show you, if you make a molecular model of this, you'll see it stays in a plane, and the bond angle is 120 degree approximately here. And I'll show you the molecules for BF3 in a minute. So here is the molecule of BF3. Boron is in the center. There are 3 fluorine atoms attached to it, and if you see, they are in a plane. So all the bonds are in the same plane. That's why they're called as planar. Trigonal is 3, and planar, it stays in the same plane. The next one is NH3. which is also called as ammonia. And if we do the Lewis dot structure, we'll have nitrogen attached to 3 hydrogens, and then there is 1 lone pair on nitrogen. So nitrogen being a central atom, it is attached to 3 other atoms, and there is a lone pair. There's just 1 lone pair here. So this is trigonal because again there are 3 bonds, but now because of the lone pair, these bonds will not be in the same plane, so they're called as trigonal pyramidal. It will form like a pyramid. So I have nitrogen here, and let's see, I have 1, 2, and 3 bonds. Let's find 3 hydrogens. So this is NH3. Now if you see, it is like a pyramid, sits on my hand like a pyramid. This is because of the lone pair which is up here on nitrogen, which pushes down the bonds down to form NH3, which is pyramidal. So to draw this, your N is a central atom, so 1 bond is in the plane. Okay, so I can hold 1 bond which is in the plane. So there are 2 bonds, 1 going out and 1 coming in. So that is trigonal pyramidal shape, and the bond angle is approximately 109.5 degrees Celsius. The last one we'll look at in this video is CH4. C is the central atom. We have 4 hydrogen atoms attached to it. So we have 4 atoms attached to it. There are 0 lone pairs on carbon here, and so we are going to find 4 hydrogens. 1, 2, 3, and 4. So this shape is called as tetrahedral. It's a one word. Tetrahedral. To draw that, carbon is in the center. I have 2 hydrogens in the plane. One is, the 3rd hydrogen is coming out. We call that as a wedge, and the last one is going in back. So let me get my hydrogen atoms. 1, 2, 3, 4. Okay, so this is the tetrahedral shape of the molecules. Tetrahedral. So if I have 2 bonds in the same plane, one which is coming out, we draw it as a wedge, like the wedge, and the one which is going behind is a dotted line, and the bond angle here is 109.5 degrees. Okay, so those are the 5 basic molecular geometry. In the next video, we will talk about the extended octet molecular geometry.